Hello. Today we're going to talk about limiting reactants, which is really just an expansion on what you've already done for stoichiometry. So if you're still struggling a little bit with stoichiometry, you're going to get more practice in limiting reactants with it. But as usual, if you super don't know what to do, please come see me in either ELT or office hours. So the idea behind limiting reactants is that in every chemical reaction, there's going to be one reactant that's going to run out first. It happens. Almost no reaction is a perfect ratio of one to another thing. One thing is always going to run out first, and that thing is called the limiting reactant. This limiting reactant is going to control the amount of product that can form, because you can't keep forming product after the limiting reactant runs out. Even if you have more of the other reactant left over, one reactant alone is not enough to form product. You need specific amounts of both. So once the limiter runs out, you're done. You can't keep making product. So to reiterate, the reaction stops as soon as that limiting reactant runs out. That excess reactant that's left over just kind of hangs out. It doesn't really do anything because there's no more reactant for it to react with, so there's just going to be extra left over. Like, think about if you were trying to make a sandwich, or several sandwiches rather, and you had bread and you had sandwich meat and you had cheese and you had condiments, but you only had 4 slices of bread. You could only make 2 sandwiches. Even if you had extra meat and extra cheese and extra of all the other stuff, you can only make 2 sandwiches because you only have 4 slices of bread. It's the same logic behind limiting reactants. You only have so much of one reactant, so no matter how much of the other one you have, you can't continue to form product. Okay, so a sample problem of what I might ask you is, I'll give you an equation, either one that you have to write out or one that I'm giving you that's already balanced, either way. And I'll say, hey, you have, say, for this example, 200 grams of S8 and 100 grams of Cl2. What's the limiting reactant and how much S2Cl2 will form? So there's a few different things that this question is saying. One, it's giving you how many grams of each reactant on the left-hand side you have. So in this example, you have 200 grams of S8 and you have 100 grams of Cl2 available to you. And I want to know, is S8 or Cl2 going to run out first? And then after you answer that question, I want to know how much product is going to form based on that information. So you might be looking at this and saying to yourself, well, there's more grams of S8 and less grams of Cl2, so obviously Cl2 is the limiter. Maybe, not always, because remember, just because one thing weighs more than another does not mean that there's more moles of it present. Because think about this, you guys, gold weighs a lot more than carbon. If I had 10 grams of gold and 10 grams of carbon, technically there's more particles of carbon there than there would be of gold because the gold atoms weigh more. So don't ever look at this and just assume that whatever there's less of the gram amount is going to be the limiting reactant automatically, because that's not always the case. Okay? So to answer this question, we really have to break it into its 2 parts. The first part is asking us, what is the limiting reactant? So the very first thing I have to do is figure out what the heck is the limiter. After I've done that, then I can deal with how much S2Cl2 will form. But first, I have to figure out which one is the limiter. And how am I going to do that? Stoichiometry. I'm going to do that using stoichiometry. I'm going to complete 2 gram to mole conversions using each reactant. Okay, so in our example, our 2 reactants are S8 and Cl2. So let me really quickly just up here rewrite our equation. Okay, so this was the equation we were using. So you might be asking yourself, why am I doing gram to mole conversions? Why is it specifically a gram to mole? And the answer to that is because in the problem, I gave you gram amounts of each reactant. If I didn't give you gram amounts of each reactant in the problem, you would be doing a different conversion. But for this one, it was listed that we had 200.0 grams of S8 available and 100.0 grams of Cl2 available. Okay, so let's start setting up our stoichiometry. For our S8, for this one, we're going to set up 1 gram to mole stoichiometry. So if we look at our formulas that I gave you in class, that's going to be a two-stepper. Our given number, which is going to be the amount of S8 used, is going to go in our upper right-hand corner, just like always. And we're going to put our placeholder 1 right there. Then after that, I'm going to need to convert that into moles. So if we go over to our handy periodic table, using our molar formula, we know that for every 1 mole of S8, that's going to weigh a certain amount of grams of S8. So we go over to our periodic table and we look at sulfur, which if you read its mass number, it has a mass of 32.06. But remember, there's 8 sulfurs present, so we have to multiply that by 8. And if we do that, we get 256.48 grams for every 1 mole of S8. Okay, then after that, our next step is to do the mole step, the mole ratio. So there's only one product in this equation, so that's the only product we could convert to. If there were 2 products, you could pick one. It doesn't really matter which one you pick, but you could pick one. So in this case, we're going to do moles of B, which in this case again is our product, our S2Cl2, over moles of A, which is S8. How do we identify A and B? B is what you're going for, A is what you came from. And then all we have to do is we have to put in the coefficients that were next to A and B. In this case, there's a nice 4 next to S2Cl2, and there's nothing next to S8, so that's going to be a 1. Okay? So all we have to do now is plug that into a calculator and get an answer. Which, if we plug that in, we're going to do 200 times 1 times 4, all divided by 256.48. And our 200.0 has 4 sig figs in it, so we're going to round to 4 sig figs. So if we do that math, we get 3.119 moles of S2Cl2 formed. Okay? So that's the first stoichiometry that we just had to do. Let me switch colors so that we can do the other one. I'm going to do the other one right down below it. Okay, so for this second one, we're using Cl2. Our given number for Cl2 is going to be our 100.0 grams Cl2. We're going to put that over a placeholder 1. Once again, this is a mass to mole conversion. So for every 1 mole of Cl2, that's going to weigh a certain amount of grams of Cl2. So we go over to our periodic table and we figure out our molar mass of Cl2. So if we look at Cl, at chlorine, we see our mass number of 35.453, but since there's a little subscript of 2 here, we got to multiply that number by 2, and we get, 70.906 grams of Cl2 for every 1 mole. Then we are going to go ahead and do our mole over mole ratio. once again, B is the same because we're still converting to that product. So we're going to have 4 moles of S2Cl2, but this time our A is different. Our A is chlorine because that's where we started. So our coefficient next to chlorine is 4 moles of Cl2, and we can do this calculation. So when we do that calculation, we do 100 times 1 times 4 divided by the product of 70.906 times 4, and we get 1.410 moles of S2Cl2. Now, once again, that 100.0 had 4 sig figs, so that's why I rounded off to 4 sig figs. Now, we look and we see which one of these is less, okay? So if we're looking at these numbers here, quite obviously, this 1.410 is less than 3.119, which means that chlorine yielded less product than sulfur. Do you see how that works? Chlorine yielded less product than sulfur, which means that Cl2 is the limiting reactant. It does not mean that S2Cl2 is the limiting reactant because it's not a reactant, it's a product. So one of the #1 errors that I see students make in identifying limiting reactants is they try and put the product because that's what you're converting to. But in reality, no. It's whatever you started with that yielded less product that is your limiting reactant, okay? So now we have identified what our limiting reactant is. But if you remember in the question, it asked us how much product was formed based on that, okay? How much product was formed. So if I go to this next slide over here and I just erase a couple of things real quick so you can see it. So in terms of calculating how much product forms, you already did that calculation. We just did 2 stoichiometries, so technically you're done. How much product formed is quite literally just the lesser of those 2 amounts. So if you recall, when we circled that this one down here was less, that's how much product is going to form. Because this amount up here cannot form because you don't have enough chlorine to make that much. You only have enough chlorine to make this much S2Cl2. So in terms of how much of our S2Cl2 is forming, that's going to be 1.410 moles of S2Cl2. Okay, I know that's a lot. I know that's a lot to throw at you, but it is quite literally just doing 2 stoichiometries and comparing them to one another. That's all that we're doing here. There is one other thing I could ask you about in terms of limiting reactants, and that is how much excess reactant is left over and or how much of it reacted in the first place. So that is an easy calculation to do. So because you care about how much of that excess reacted in the first place and how much of it is left over. If you recall from my initial notes, I told you that we use stoichiometry to make sure that we don't waste reactants. This is why, because if you're reacting a bunch of extra sulfur that you don't need, you're just wasting it because you're contaminating it with a couple of other things. And even though that sulfur is unreacted and left over, it's still really hard to isolate it by itself. So to figure out the excess that reacted, all you have to do is complete a conversion from the limiting reactant to the excess reactant. So more stoichiometry is what I'm telling you. All you have to do for the instance of our sample problem, which once again, let me go ahead and rewrite that equation. Up here, we already identified that Cl2, was our limiting reactant. We know that Cl2 is our limiting reactant. We also know how much Cl2 we started from. We started with 100.0 grams of Cl2. So to tell how much S8 reacted, all I have to do is a conversion from Cl2 to S8. That's it. Okay? So I can theoretically do this a couple of ways. I could do a mass to mass if the problem asks for it. So if I said how many grams of S8 reacted, then you would have to do a mass to mass because you know how many grams of Cl2 you started with, and I'm asking for mass. But if I just say how much, you could give me that answer in moles. You don't have to do mass to mass unless the problem asks you for it. So in this case, I'm going to go ahead and do another mass to moles because why not? I know that I started with 100.0 grams of Cl2. I want to know how much S8. Okay, so what are we going to do? We're going to convert it. What I have to do first is convert this grams into moles of Cl2. So for every 1 mole of Cl2, that's so many grams of Cl2, which that number we already figured out in the previous stoichiometry. It was 70.906 grams for every 1 mole. So we don't have to do that math again. In terms of doing our mole to mole ratio, we just look at the equation again. Your target one, B, what you're going for, there's no coefficient next to that. So that's just going to be 1 mole of S8. Where you came from, Cl2, there's a 4 next to it. So you're going to put 4 there. And we're going to do our calculation. Which, if you plug all that into your calculator, you're doing 100 times 1 times 1 divided by your product of 70.906 times 4. And that is going to give you 0.35 moles. Or sorry, excuse me, 0.35 to 6 because of sig figs. Now, we know how many moles of reactant was used. Okay, we know how many moles of S8 was used. But that may not be all I ask you. If I say how much was used, then great, that's the answer. If I say how much was left over, on the other hand, that would be a different conversion entirely, because if I want to know how much was left over, and you know that we started with 200.0 grams of S8, in that case, you would have to do a mass to mass conversion from Cl2 to S8 and then subtract, okay? So let's pretend for a second that we carried this conversion one step further. Let's pretend we did a mass to mass, okay? So if I want to know grams of S8 and I want to convert out of moles of S8, I just need to flop that molar mass conversion according to the formulas that I gave you. So for every 1 mole of S8, that's going to be so many grams, which we should have already figured out way back when we were doing that initial conversion. So if we look on the periodic table, we see that sulfur weighs 34.06. All we got to do is multiply that number by 8, which on our calculator is going to give us 256.48 grams of S8. So we just do our calculation once more through, and we do 100 times 1 times 1 times 256.48 divided by our product of 70.906 times 4. We get 90.43 grams of S8 was used. So real quick, I just want to recap and say the conversion I did before from mass to moles That would be what you would use if it just says how much was used. If it said how much was used in grams, you would do this one. So once again, you have to pay attention to what the problem is asking you for and do your conversions accordingly, okay? If I want to know how much excess reactant was left over, you're still gonna do this, and all that you have to do is subtract this number from how much excess reactant you started with, okay? So subtract 90.43 grams from the initial 200 grams. So if we did that on our calculator, we would just do 200 minus 90.43, and we would get 109.57 grams of S8 left over. Once again, yes, we would round that to the appropriate amount of sig figs, so you're going to get 109.6 grams of S8 remain. Yes, I know that that is a lot of information. Yes, I know that you are probably not comfortable with stoichiometry yet. However, this will give you a lot of practice. So what I'm really trying to get across to you is that you can use stoichiometry to figure out how much product will form. You can use it to figure out which reactant is going to limit your amount of product. You can use it to figure out how much of each reactant you could use. Okay, so there's a lot of uses for it. And don't worry, because we're going to be doing a lot of practice with this, and I'll have keys as usual.